recap what we did last time. We talked a little bit about curves and we evaluated a curve at a t parameter. So let's go ahead and do that again. Part of this is just being repetitive so that we learn some good habits. And so the first thing we need to do, right, if I'm going to do something with one of these curves in the Rhino native modeling environment, is bring them into Grasshopper. And so, again, we did this before, but I'm just going to keep going over this again and again and again, try to drill it in your head. Parameters tab, geometry, right? Here I have some placeholder widgets for particular parts of geometry, in this case a curve. And so what I can do is use this widget and I can bring in one or more curves from Rhino and then reference them in Grasshopper. Okay, so I can take this curve that I've already drawn in Rhino and I can build off of it parametrically in Grasshopper now. There's the curve as an ingredient, and then I get ready to be plugged in for an input for some other widget. Okay, and so let's do this one more time. We're going to evaluate the curve at a t parameter. Again, just to explain what we're doing here, I'm going to get the evaluate curve widget out. Okay, and so it first of all wants the curve to evaluate. That makes sense, right? And we talked about the t parameter before as the sort of street address. So if you think about a curve as a road, and we think about how we find specific locations along a road, which is a linear sort of thing, right? We usually typically use a street address, and we move one way along the road, and the street address steps upwards. We move a different way along the road, the street address numerically sort of gets lower. And so you can think of the t parameter as an address that we can use to find a specific location on any curve. Okay, and typically what we do is we try to normalize the curve between 0 and 1. So it makes it that much easier for us to figure out where the halfway points are and things like that. You know, as you know from drawing in Rhino and AutoCAD and those sorts of things, it's really helpful sometimes to find a midpoint or endpoint, right? And in fact, that's what object snaps allow us to do when we're manually drawing things with our mouse. Here it's no different, except we specify things with a number. Right, so halfway along a curve, a midpoint of a curve would be 0.5 for the t parameter. So we'll go ahead and do this. I'm going to plug the curve in, right? And I'm going to right click on this C, right? This is the input for our evaluate curve widget. I'm going to right click and it brings up a set of options for what I can do with what the curve that I'm plugging in here. And I'm going to select reparameterize. I talked about this before. What that does is it takes whatever that midpoint the start point and end point of that curve, right? The start point might be 0, and you know, if this thing is 50 units long, then you know the end point might be 50.196. What it does is it normalizes them so that the curve starts at 0 and ends at 1, which makes it a lot easier for us. Okay, so you just have to get used to right-clicking and toggling that reparameterize button. Okay, and don't worry, you wouldn't be the first to forget to do that on occasion, and sometimes we can laugh about it after the fact when something's not working and you're looking at it and really frustrated, and they go, "Oh, you just forgot to reparameterize." Okay, so you can see here I'm passing along a curve, and I'm passing along a particular t parameter. And what it does is this widget looks at the curve, and it finds the address that we are giving it for the t parameter, and it finds the location along the curve, and then it places a point there on the curve, okay, at that location. So if we want to go all the way to the start point, we can go to 0. End point would be 1. Midway point would be 0.5-ish. There we go. And so not only does it find that location, and not only does it place a point at that location, right? So this is one way to populate a curve with a point. But it also finds some other properties of the curve at this location, right? So it also gives us the tangent. I don't know if you guys remember what tangents are from your days in high school geometry, but let's talk about that. So instead of using a straight line, I'm going to go ahead and reference this curve, this planar curve right here, and let's take a look at that one. So I'm going to set one curve. I'm right-clicking, and I'm going to change it to use that curve. Okay. We made a change in this ingredient, and so that change, all the information that we change propagates from left to right, right? And so you can see now we're actually finding the 0.5 t parameter on this curve now, and placing a point along it. And so what I'm going to do is I'm going to draw a line from this point, and I'm going to use the direction of the tangent that it's finding, just so we can draw a tangent line, and so you can visualize what a tangent really is, okay? And so just pay attention. I'm just going to find a way to draw this tangent. This is one of many ways I can draw a line in Grasshopper, and we'll talk about that more, trust me. And so this is a start point for the line, a direction, and then a length. So the direction, I'm going to use the tangent direction. And then for the length, I'm just going to beef this up so it's a little easier to see, maybe make it like 15 or so units. Okay. Now, over here in Rhino, I'm going to zoom in so we can see this line. Okay, this is the tangent. And actually, you know what? I'm just going to make a copy of this, and I'll also draw this line in the other direction, just so it's a little easier for us to see. You don't have to worry necessarily about what I'm doing. I just want to sort of make sure you guys understand what I mean when I say tangent. So you'll see this tangent, it's green because it's highlighted. And I'm going to move the t parameter. You can see, right, that the tangency changes, right? Yeah. And so, you know, we're dealing with curves and freeform curves and splines. I mean, there's a whole branch of mathematics devoted to this. It's called calculus. For those of you who had some high school or college calculus, you know that there's ways to calculate the slope of a curve at any given point, right? And what's nice about calculus is that, you know, we understand that this curve, the curvature changes, and so that slope actually changes at each discrete point along it, right? So here you can begin to see, but essentially for all practical purposes, if we're going to define tangent for our class, we'll call it the measurement of the slope of the curve at any given point, okay? All right, look at that. Okay. Great. Now I'm going to move on to this more interesting curve. It's three-dimensional. So you can see that the curve that we were working on, it's highlighted now in yellow, that is a planar curve. It's all in the XY plane. This one's a little more interesting. It's more three-dimensional. It's sort of moving in all three directions at once in any given time here. More akin to you know, like a roller coaster track or something like that. And so I'm going to go ahead and reference this curve instead. I'm going to say set one curve, and there we have it. Okay, so now you can see that this tangent's going to change pretty dramatically as we run across this curve. All right, great. Okay, let's see. Now I have a couple of pre-baked files here, right? And so one of the things we didn't talk about is not only can we place a point along a curve at a t parameter, but we can also place the perpendicular frame at that t parameter. Okay, and so let me go back to the unnamed thing I was working on here. I'm going to go ahead and delete this stuff now. We already know what the tangent is. We've already identified a point. If I go to analysis again, not only is there evaluate the curve at a t parameter, but there's also solve the perpendicular frame at a curve t parameter. Okay, and so what this does is this begins to find the perpendicular frame. So it places a plane in the direction that's perpendicular to the curve. Okay. Essentially, this plane, the orientation of this plane is perpendicular to the tangent that we just defined. Okay, this is called a normal plane, right? Normal meaning perpendicular. If you remember that from hopefully high school math. So I'm going to go ahead and plug in this curve, okay? I'm going to go ahead and use the t parameter. Now watch what happens, right? This is what I was talking about with that reparameterize option. What happens if I don't reparameterize the curve? Turns out our curve by default is longer than 0 to 1. It's like 0 to 15 or something. So I want to reparameterize, make sure I reparameterize that so that the 1 goes all the way to the edge. Let me move my model space here so we can see the entire curve, right? Now I'm placing this plane at that t parameter, and it's querying the properties of that curve and finding the frame orientation that's perpendicular to the curve. Okay, and so look at that. All right, and so you can see that, basically as the curvature of the curve changes, also that the orientation of the curve's normal changes as well. And of course, we also talked about how the tangent changes along the curve as it's measuring slope and how the slope changes as we move across the curve. It's a lot to say in one sentence, but okay. You can always slow this down or repeat it. Okay. And so this is one of the example files I'm giving you in a zip folder, which basically is doing some of the things that we did before. Finding a t parameter along a line, finding a t parameter or t address along a curve, but then placing a perpendicular frame along it. And here we are doing the same thing for this three-dimensional curve. I also drew the tangent line for you, so you can sort of see all of this information all at once, right? So the computer is computing all of this and querying all this information for you in real time, and then redrawing everything accordingly. Okay. Let's do a few more things with curves. Here's another one. This one's called divide curve. So we've been using t parameter, evaluate curve at t parameter, and place a perpendicular frame at a t parameter along a curve in the analysis tool set. If we go to division, we have another set of tools, right? So we can find, let's see, divide curve. Okay. Also, we have curve frames and perpendicular frames, right? And so if we want to, let's say, find more than one point or one location along a curve, or we want to populate the curve with more than one perpendicular plane, we can use the curve division tools, right? Okay, let me go ahead and delete this and we'll start over again. So here's my curve, and I'm going to divide this curve, okay? And so let's look at the inputs for this widget. First of all, it needs the curve to divide. That's obviously the main ingredient here. What else does it need? It needs a parameter, numerical parameter, saying how many segments do you want to divide this curve up into, right? That seems fairly easy. I already have the number slider made, right? So if you go to the params tab, you can find that number slider. And I've constrained it to integers. If you double click on the label, remember you bring up the properties box and you can change some of the properties of the number slider. I'm going to constrain it to integers. So I'm going to plug in this curve. I'm going to plug in the number of times to divide it. And then I can change the number of divisions. You can see, right, it's divided up into 33 segments. And each of those segments each of those divisions actually are populated with a point, okay? So if you can imagine this just for a second, if I'm dividing this up into 33 segments, I actually end up with 34 points. And that's what it tells me, right? If I hover my mouse cursor over the output here, right? It tells me, ta-da, there we go, 34 locally defined values, 34 points basically. Each of those numbers inside those parentheses are a coordinate for a point. So, of course, it also gives us, again, the tangency vectors at each of those points, each of those locations. Okay, I can do the same thing and find or populate each of these with perpendicular frames, right? And so now it's just a number. It's the parameter game of defining how many times we divide this curve up, and then at each of those divisions, our curve is populated with both a point and a perpendicular frame at each of those points. Yay! Isn't that wonderful? All right. Let's see. I'm going to go ahead and close that without saving so I don't accidentally mess something up here. Close this one as well. All right, I have a few more. So with this one, no, it's basically the same thing we just did, right? Populate this with points and frames at the same time. All right, now I keep mentioning or calling this three-dimensional curve a roller coaster track. So let's start building something off of it, which I think it could be kind of interesting. Okay, maybe we can actually make a set of little cross struts and then make a second rail in 3 dimensions and actually make this look like a roller coaster track. Okay, and so this will be the precursor to us really doing, I think, maybe some more sophisticated things with curves next. So let me just quickly go over the recipe, and so maybe it helps for us to sort of understand what we're going to do before we actually build this from scratch. I have taken this curve in Rhino and I've referenced it into Grasshopper so I can build off of it. Okay, and this is the divide curve tool. Okay, I can go ahead and get rid of this for right now. Here's what we really want, right? We're going to divide the curve and populate each of those divisions with perpendicular frames, okay? And so I've plugged in the curve, and I've plugged in a number slider that we can use to adjust the number of divisions, right? So we can make this much less dense or much more dense, right, depending on how we manipulate that slider. Okay, that gives us a set of frames, right, a set of planes, basically. And here, let me just zoom in. Let's see if we can, I've turned the preview off on these, but you can see each of these planes. This is just a visual representation of a plane that actually extends infinitely into space in all directions, okay? So it's kind of helpful, though, just to be able to see it as a little, plane that's trimmed within a frame, all right? Now I'm going to look at each of these planes. Each of these planes has its own, and I'm trying to, sorry about this, let me see if I can rearrange this a little bit. What I'm trying to do is zoom in on one of these planes so you can see it just a little better. Let me see if I can maybe go to the end here. Okay, so, there we are. So you can see this plane. Each of these planes has an x and a y coordinate of their own, right? So this is the x-axis, this is the y-axis, let's say. And so what we want to do is maybe just get each of the axes from these planes, right? And we can use those as directions to actually draw a line, okay? And so what I'm going to do is I'm going to find the properties. I'm going to break the planes apart into their x, y, and z constituents and then use that x direction, right, to create lines, all right? And then after that I can draw the lines, which is what this does. So I use a start point, then a direction, then a length. All right, so let me go ahead and start this one from scratch, and we'll build this thing up step by step. First step, well, I have a curve in Rhino and I need to bring it into Grasshopper. So I'm going to go to the Params tab, Geometry, Curve Widget. I'm going to place that in. I'm going to right click on the curve widget and find Set One Curve. I'm going to go ahead and click in Rhino, the curve that I want. All right, now I can see that it's highlighted green when I select the widget that references it, so I know that I'm using the right curve in Grasshopper now. And I want to divide the curve, so we go to Curve tab, right, and Division, and I'm going to find the Perpendicular Frames Division tool here. Go ahead and divide this curve. Now I think by default the number of divisions is set to 10. I want to change that. I want to be able to make more divisions. I'm going to make a number slider, Params tab again, number slider. I'm going to double click on the label. I'm going to change this minimum. Again, this is a division operation. I don't want to divide 0 times ever. So I'll set the minimum to 1, the maximum to 100 or something like that. It'll give me a lot more latitude in sort of adjusting how many of these I really want, right? So now I can really beef this up if I want to. All right, so just like my XY plane here, it has an axis. There's the x-axis, here's the y-axis, and then there's a z-axis that's implied. It's not really drawn. Each of these planes have their own x, y, and z Cartesian system, right? And so I'm going to try to pull out the x directions for each of these planes that we've created. Okay? And so I'm going to go to Vector, and I'm going to look at the plane tools, and here's how I can construct planes from x and y axes. Let me see if I can figure out a way to sort of deconstruct the plane. Oh, here it is. Deconstruct the plane into its component parts. So what this will let us do is understand the exact origin of the center point of this plane, where that's located in space, and then the x direction, the y direction, the z direction. That would help us rebuild this if we wanted to. But let me see. Okay, so I have a curve. I divided the curve 45 times. It's going to give us 46 frames, right? I plugged in 46 frames to find 46 x-axis vectors, all right? Now I'm going to draw 46 curves, one along each of those x-axis vectors, okay? So I'm going to go to Curves, and I'm going to make a line from start point, direction, and length. This will be my origin, start point. This will be my direction. And now for length, I want to go ahead and make that again a variable that I can change. I'll go ahead and up the max just in case I need to. Go ahead and do that now. And I'll use that for length. Okay. Now there's one other thing I'm going to do here. These planes, they're really like visually intrusive. It's hard to see anything else but these planes. So I'm going to right click on them and turn their preview off. They're still there. They'll still be computed. We've turned them off because it's visual clutter right now. And so I want to be able to see these things. So as you can see, now we're drawing these lines, and I can, of course, make them longer. Yeah. All right. Great, great, great. Okay. And so last but not least, I need to make the other side of this track. Whoa, nice. Okay, so there's several different ways I can do this, but the easiest way might be to, hear me out here. So I have all of these lines. They're now highlighted in green. And I drew them by finding a start point and then defining a vector, right? Basically a direction and a length or magnitude. And so if I find each of these lines endpoints, then I can connect those up with a spline and create the sort of offset version of this curve. So I'm going to go ahead and do that. I have a set of curves that I've already made. So I'm going to go to Curve tabs. In this case, I'm going to analyze the curve to find each one's endpoint. Okay, there it is. There's 46 endpoints. You can see them highlighted in green now. And so now I just need to find a way to make a nice spline. I'm going to use an interpolated curve. Okay. And for the vertices for this interpolated curve, I'm going to pass this list of endpoints, 46 of them. And there we go. Okay, I'll go ahead and turn the preview for these points off, and you can see our brand new curve. Yeah, look at that. Okay, and now, it seems like the shape of this curve is also dependent on the density of the number of points that we're sampling along the original curve, right? And of course also how long our perpendicular struts are. Excellent. All right. So that's a little bit of just fun with curves. And what we did is we started to populate the curves with points and with planes, and then drawing things from those points and planes. All right. And so I think maybe you can start to understand a little bit about where we're going with this, right? Because we're going to start building, things with lots of different sort of struts, and there's lots of linear components, things like trusses and lattices. And so I just wanted to sort of touch on this a little bit more as far as like how curves work. I highly recommend that you rewatch this and this time you pause and sort of try to follow along back at your computer. As well, I've tried my best to label all of these example files that I've opened and provide them to you on the website so that you can actually open these up. So if you get stuck or you want to open up the examples that I showed, and look at those first, feel free, okay? And so I'm just really curious and interested in making sure that you're learning. But then also I want you to sort of go back and try to do this and follow along with your own file, your own new file, okay? That practice, while you won't remember everything all at once, that practice will help, right? And will engender some really, I think, very positive habits, like remembering how to bring in geometry from Rhino with this params geometry set of widgets. Whenever we try to find particular locations along a curve, that we reparameterize that curve, right? And just sort of getting the muscle memory down as far as how to begin to deal with Grasshopper and how to build one of these things, right? And so it's like, here's my starting ingredient, and here's what I want to end up with at the end. And it's always a chore sort of trying to figure out, like, how do you get from the beginning to the end, right? That's an algorithm, right? So this is a routine that we defined. We take a curve, and then we divide it. We build a bunch of lines off of it, and then we connect up the endpoints of those lines in order to create some sort of offset version. Okay?